All right, so let's talk about data design, right? So we've been just covering just some of the basic definitions of what tables are, fields, and foreign keys and primary keys. We saw that somehow we decided on those five particular tables. So we'd like to discuss, and well, how is it that we came to decide that it was those five particular tables that we decided on? Also, I want to formalize the definition of what class diagrams are and how is that we're going to document these structures. Up to this point, we've used schemas definitions as just saying, well, it's the name of the table plus the list of all the fields, right? And a nomenclature. Now that textual representation is certainly useful, but a graphical representation can certainly add to our tool set. So let's consider a really trivial um, data definition where we have maybe we have a set of CDs, right? And we that we want to enter into our database, and we initially come up with our understanding of how CDs work, right? Lead us to this initial data representation, right? We said, well, we'll need a record where we can type in the name of the CD, and perhaps I want to go a little further. I want to also capture all the songs in that CD, right? That seems a very sensible first step at this, right? So we have a CD table with a unique CD ID, a unique identifier with the title of the CD, the release year, the band, the genre. And then underneath, we have all the songs that belong to each one of those CDs. So it's a track ID that uniquely identifies this track, this song. And then the CD that it belongs to, right? Where is this song? In which CD does it appear? The track number 1, 2, 3, and so on and so forth, the title of the song, and how long is the song. Yes? And that's fine. I mean, I start entering my CDs, and I'm halfway through, and I find a CD that does not fit into this. Right? It's a CD that actually doesn't have just one band; it has multiple bands. Right? Or I find a particular band that was experimented with all sorts of genre. Right? And so now it doesn't fit into the same genre. Right? So now I have a conundrum. It says, well, what do I do? Right. So my original data set representation on how I was going to plan on splitting this doesn't fit my data set. Right. Right. So when you come to the a best of CD with tracks from various CDs, right? A whole bunch of songs from different it's a band that's been around for quite a while, and now it's gathering a whole bunch of songs from many different CDs. Right? How do I capture that? Now I'm introducing redundancy because of that a particular song will be represented multiple times, right, across many CDs, right? And so as far as the database is concerned, these are separate songs, even though the titles might be identical, right? So how do I do that? Or I'm going to burn my own CD, right, where I have some rock, some merengue, some salsa. So now it's a mixture of a whole bunch of different genres, and or different bands, right? Or how do I do this? So usually, oftentimes, it's really hard to do data design starting from a schema, right? Starting from this textual representation of the schema. It is usually much easier if we are able to instead represent it in some graphical form, right? Where we can draw some lines, some boxes, and move some fields around, and split up a box into two different boxes and move some of the fields around, right? So what we're going to try and do is to find a different way of representing them into what we're going to refer to as a class diagram. All right. So class diagrams are one of the most useful types of diagrams in the UML, Unified Modeling Language. The UML is a very popular language, graphical language that allows engineers of all different types to collaborate, regardless of what particular language you're familiar with, what particular where in the data stack you are, where in the technology stack you are. We can all talk about how the data is structured, regardless of what our backgrounds might be. Right. So UMLs is very popular, and class diagrams in particular are going to allow us to capture what are the entities, right? What are the things that we're capturing, the ideas, the concepts, right? CDs or tracks, those are all entities. What are the fields in there? What are the attributes of each one of these data sets? And how are they related to one another? So class is a type of entity, like CD, like humans, animals, desks, buildings. Those are all classes representing real phenomena in the real world. So UML class diagrams allows us to represent them in this graphical representation, and we need to be able to go back and forth between this very abstract graphical representation, right, where we're drawing boxes and arrows and whatnot. We need to go and be able to convert between this nice graphical representation and a concrete implementation where you're going to type it into a database. Yes, you need to be able to go back and forth, right? What we'll find is that not everything is transferable, since class diagrams capture many more different concepts, much more modern concepts that are not in the original relational databases that were designed several decades ago, right? So databases were designed when object orientation was still very theoretical. Today, object orientation is widely used and understood, but relational database never caught on, right, or caught up to those concepts that came later, right? So there are many things that can be captured conceptually in a UML diagram, but are not necessarily transferable to a relational database, right? Nevertheless, we need to be able to see, well, what can we do? How can we map these two different worlds? Okay, so we're gonna first look at the UML and see how we convert it. We can convert it to tables, and vice versa. Starting from tables, how can we represent it in UML class diagrams? We need to go back and forth. So here's a class diagram that we're going to be considering for a really simple database. We have the student representing all the students, and notice that we have the attributes of all of those students. We have the student name, they have the graduation year. For the department, we have the department name. For the course, we have the title section. We have a professor and the year that was offered, and the enrollment. We have the grade. All right. Notice what's missing from here, right, are the keys. See that? The keys are missing, right? Those instead are representing using those lines, right? The keys are replaced by connecting these boxes using these lines and these numbers and stars around them. See that? Okay. So for instance, the fact that we have here a star next to the student and a 1 on the department, this tells me that for every one department, there are a whole bunch of students that are related to one department. See that? So that arrow is saying that there is an association, there is a relationship between these two, between records from these two different types of entities, right? One entity in the department is related to 0 or many students and instances of the student. Make sense? That's what the 1 and star mean over there. Same thing for the course and the section. We're saying that for every course, every single instance of a course is related to 0 or more sections, right? Same thing for the department. For every one department, you can have many different 0 or many courses. The one that is kind of a little weird here is the enrollment. The enrollment says that for every one student, you can have many different enrollments, meaning one student can be enrolled in multiple things, right? What can be enrolled in? Oh, in a particular section, right? And so the other side says that one section can also have a whole bunch of enrollments. What are things that are enrolled? Oh, students, a particular student. Yes. So the enrollment really is playing the role here of an association class. It's saying that, hey, that student over there it can be related to many of those sections over there, right? Or vice versa. This section over here can be associated with a whole bunch of students, right? So we often refer to this as a many-to-many association, right? This is a many-to-many table, right, which are pointing to both of them. It says, hey, that student is enrolled with that section, and that section is enrolled with that student, right? Not necessarily the same one, right? So it's a many-to-many relationship here, and a many-to-many relationship is typically implemented as two one-to-many relationships. We say that this association is a one-to-many, right? And notice that we have a whole bunch of one-to-manys, one-to-many, 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 and so on and so forth. So one many-to-many usually is implemented as two one-to-manys, right? Now, we could have If we didn't have grade here, UML would be just fine, right? Drawing an association just between student and section, just a line between student and section, and putting star on either end. All right, it's a many to many. One student is associated to many sections, one section is associated to many students, and we call it a day, and we're done, right? But because we have an extra field, grade, right, we don't have any place to put it, right? So we need an additional entity to capture the data plus the association. Make sense, right? Also, say we didn't have grade. Say we didn't have grade, and we just have an arrow or line between student and section, right? Well, there is no way to implement in a database this line, right? There's no way to implement that, right? The only way to implement it is to have a dedicated table that has two foreign keys that point to the other two, right? Right. So going from just a single line to an additional class, okay, so that we can then go in and implement it in a relational database. We usually refer to that as making something from abstract down to a concrete implementation. We call that reify, to make concrete, something that is conceptually aligned, right? We are making into a concrete class that can be converted into a concrete table, okay? All right, so we'll see a couple examples of this. Yes? Yeah, it's a one-to-one. Yep. And notice that it's a 0.1. That means that it could be 0, meaning no permit, right? A student could say, well, I don't want a permit. I'm not driving in, right? So it's an optional. We say that it's an optional relationship. Yep. Yep. So these 1 and star and 0.1 and whatnot, we call that cardinality. How many of these are participating in the relationship, right? So the general nomenclature is to say n.m, meaning n being the minimum number of entities that are participating, and m being the maximum number of entities that are participating. How many students are participating? Here, typically, it's just 1, right? And so also a couple of the nomenclatures. Star is denotes 0 or more, right? It's a shorthand for saying 0.star, right? So star, usually we use it as a shorthand of saying n being 0 and m being many, right? So 0 to many. 1 is also a shorthand by saying n is 1 and m is 1. Usually we use a shorthand version of just 1. Okay, those are the most common values, right? So we create these shorthand for saying that, right? So the most common one is just 1, star, 0.1 are the most common ones, and we refer to them as annotations. We are annotating these classes. So there's a few very common types of relationship. One of the more common ones is the one-to-many, right? Where you have a one, there's definitely one of them on this side of the relationship. There's definitely a department. There might not be any students enrolled in that department, right? Or there might be 1,000 students are related, right? So this star means 0 or more, right? So there's one to many, where the many could be 0. Okay. So again, this is a very common. We can refer to it in both directions. We could say it's a one to many or a many to one. The more common way we refer to it is just a one to many, right? But you will also hear many to one as well. Okay. The other one that are also very common is a one to one, saying that a student must have a permit. So this says I have a student. Well, they also have a permit. It's a 1 and a 1. Okay, everybody has to have a permit, right? Or I can say that it's optional, right? Instead, it's a 0 to 1, right? Meaning maybe there's a permit, maybe there's not a permit. Okay, so it's optional for you to have a record saying that you're driving in and parking, or I'm not. I'm taking the public transit. Also very common. It's a many to many, right? Where you might, for instance, allow students to be enrolled in multiple departments. Maybe I have a major in computer science and a minor in math or something, right? And I might be enrolled in both departments, right? So a student can be in many departments and a department can have many students, right? So very, very common. Now some jargon. When you have a star, it means that you don't know how many are participating. It could be none, right? Whereas if you have an actual value, like a 1 or 2 or 3, right, where you have an actual value, you know how many are participating, we say that that's a strong relationship. We know how many, right? The force is strong with this one, right? There's many, and you know how many there are. Whereas over here, I don't know how many. There might be none or a whole bunch of them. So we say that this is a weak relationship, right? So this is a strong to a weak relationship, okay? Also, here as well, right? 1 to 1, that's a strong to strong relationship. Whereas here is a strong to a weak relationship. I don't know how many. Maybe there's none. Maybe there's nobody here, or maybe there's one. So it's a strong to a weak relationship. Okay. Again, some nomenclature, some jargon. So many to many is a weak to weak as well. 1 to 1 is a strong. 0 1 is also might be weak. So here's just a couple of ones. Weak to strong. Star to 1, or optional to a 1, or strong weak. We have 1 to many, 1 to 0 1, or weak weak, or strong strong. Okay, it's just some example on the nomenclature.